You know, the internet is basically this one gigantic haystack of information. So how in the world do services like Google find that one single needle, a copied article, among billions and billions of other pages? Well, in this explainer, we're going to peek under the hood and actually build the machine that does exactly that.
So this is the core problem we're trying to solve, right? And it's not just about finding perfectly identical copies. That's the easy part. The real challenge is finding documents that are almost the same, the ones that share huge chunks of text, even if some parts are shuffled around. That's the real trick.
Now your first instinct, my first instinct, would be to just do the simple thing. Compare every single document to every other single document. It's the straightforward brute force approach. But as you're about to see, when your haystack is the size of the entire internet, simple well, it completely falls apart.
I mean, just think about it. For a pretty small set of only 100,000 documents, you're already looking at 10 billion comparisons. If you scale that up to 1 million documents, that number just explodes into the trillions. You'd be waiting for years. It's a non-starter, computationally impossible. We need something way, way smarter.
All right, so to build this similarity machine of ours, we have to crack 3 big challenges. First, how do we even get a computer to understand what a document is? We got to turn text into numbers. Second, once we have those numbers, how can we compare them instantly? And third, the big one, how do we get around that whole 10 billion comparison nightmare? Let's break them down one by one.
Okay, first things first. How do we turn these pages of words into something a computer can actually work with and measure? The whole idea is to create a unique digital fingerprint for every single document out there.
And the tool for the job here is something called shingling. A K-shingle is just a chunk of a document of a specific length, K. Just imagine sliding a little window across the text and taking a snapshot every time you move it. That's basically a shingle.
Let's make this real with a quick example. Say our document is just the word eBay, and we decide our shingle size, our little window, is 3 characters long. So we just slide that window across. The first chunk is eBay. Move it one spot, you get BIA. Move it again, you get EAB. So the final set of unique shingles is just those 3, eBay, BIA, EAB. And boom, that's our document's fingerprint.
And there you have it. Problem 1 solved. We have our fingerprint. Now we can just look at how many shingles 2 documents have in common to see how similar they are. Simple, right? Well, there is a problem. For a real document, like a news article, this fingerprint isn't just a few items, it's absolutely massive.
Okay, so we've got these giant fingerprints. How on earth are we supposed to compare them without grinding everything to a halt? This leads us straight into challenge number 2. How do we shrink this thing down, but, and this is crucial, keep the similarity information intact? So on one hand, you've got the full fingerprint. It's perfectly accurate, but it's way too slow to compare when you have billions of them. What we really want is what's on the other side, a tiny, compact signature that's super fast to compare. But the big question is, can we actually make that smaller version without losing the accuracy we need?
Well, it turns out the answer is a big yes, and it's thanks to this really elegant trick called min-hashing. And this is where the magic happens. Min-hashing creates these tiny signatures with this amazing mathematical guarantee. Now, Jaccard's similarity sounds complicated, but it's really just a simple score of how much 2 sets overlap. And what's so cool is that min-hashing preserves that exact score, even in the tiny signature.
And you can't overstate how powerful this is. We can literally take a document with millions of these shingles and squash its entire fingerprint down to a signature of maybe just 100 numbers. We've gone from this huge, messy set to a nice, neat little list of integers.
And just like that, challenge number 2 is toast. Because now we can just compare these little 100-number signatures, and the comparison is practically instant. In computer science terms, we call this a constant time, or O1 operation. What that means for us is that it doesn't matter if the document is a tweet or an entire novel, the comparison takes the same tiny fraction of a second. This is a huge, huge win for speed.
Okay, we're getting close, but we're not quite there yet. We still have that final, massive hurdle to overcome. We have instant comparisons, which is great, but we still have billions of documents. And this is where the true genius of the system really shines.
Right, even if each comparison is instantaneous, trying to compare every single document to every other one is that same insane math problem we started with. It's just not going to fly. What we need is a clever way to find the likely matches without having to check everyone.
And the solution to this is a technique called Locality-Sensitive Hashing, or LSH for short. The core idea is actually pretty intuitive.
LSH is basically a special kind of sorting system. It's designed so that similar items have a really high chance of being thrown into the same bucket, while dissimilar items get sorted into different ones. It's a way to pre-sort our signatures by similarity.
So how does this sorting actually work in practice? Well, we take our little signature of, say, 100 numbers, and we chop it up into smaller pieces. We call these pieces bands. Now, take a look here. Document A and document C, their full signatures are different, but if you zoom in on just band 1, you'll see that that little chunk is exactly the same, XYZ.
And that right there, that's the simple rule that makes this whole thing possible. Instead of comparing every single pair, the new rule is this: we only compare documents if they match on any single band. We call these candidate pairs. This slashes the number of comparisons we have to do, letting us focus only on the pairs that are most likely to be a match.
And that's it. We've built all the pieces, so let's put it all together and see our finished similarity machine in action.
So here's the entire pipeline, from start to finish. First, shingling takes the raw text and turns it into those big, unique fingerprints. Then, min-hashing comes in and shrinks those massive fingerprints down into small, super-fast signatures. And finally, LSH does the clever sorting, grouping similar signatures together so we only have to check the most promising candidate pairs.
Now, in a perfect world, this machine would work like a light switch. You know, like the graph on the left. It would perfectly find every similar pair and completely ignore every dissimilar one. But in the real world, it's more like a dimmer switch, which is what that S-curve on the right represents. It's a system based on probability, not certainty, and that means we have to be smart about some trade-offs.
This S-curve is really the heart of LSH. See that yellow area? Those are our false negatives, documents that are actually similar but our system might miss them. And the green area? Those are the false positives, dissimilar documents that our system flags for a final check anyway. The whole game is about tuning the system, like by changing the number of bands, to shrink both of those areas as much as possible and get that curve as steep and as close to that perfect light switch as we can.
And you know, this whole similarity machine isn't just for finding plagiarized articles. This exact same logic, it's what powers product recommendations on Amazon, grouping you with shoppers who have similar tastes. It's what clusters thousands of news articles about the same breaking story. It is a fundamental engine of the modern internet. So now that you know how it works, the real question is, where are you going to spot it next?